let's begin thinking about surfaces in space. And as an introduction, I want to ask you to consider x equals 3. And recall back when you were first introduced to the number line and you were told, well, sketch this point x equals 3. What you would do is you would just go over here to the 3 and make a dot because it was just one dimensional. All you had was the horizontal axis. Then you were introduced to 2 dimensions, the y-axis, and then if you were asked to graph x equals 3, you wouldn't just make a dot there, you would make a vertical line that passes through 3 and is parallel to the y-axis. Well, now we want to transition to 3 dimensions, and we want to have that same problem. We have x equals 3. And we want to see if we can determine, well, what does this mean? Because now, whereas when you graphed x equals 3 and you had the x and the y-axis, what you did was you graphed a line that was parallel to the y-axis. Now let's see what happens here. Well, if we have x equals 3, we certainly want the whatever we're graphing to pass through 3. And what this is saying, just like when we graphed x equals 3 in the 2 dimensions, we were saying, it doesn't matter what y is. X is always 3. So what about when y is 3? Well, x is 3. What about when y is 4? X is 3. So we get a line that's parallel. Well, if we're in 3 dimensions, then x is always 3. It doesn't matter what z is or what y is. So now we have 2 things that we don't care what they are. X is always 3. Well, if you think about it, that would form a plane. For all the x's and y's, for all the y's and z's, x is always 3. And we might be able to sketch a representation of that with this paper here. I go over to 3, and there's a line passing through there, passing through 3. And then I could go this direction parallel to the y-axis. And then down here go parallel to the y-axis. And then parallel to the z-axis. Maybe go down here. And this is kind of a representation of the plane. This is how we might be able to represent it. Notice, no matter what no matter what y and z are, we always have x is equal to 3. So that would be a plane that just passes through x equals 3. It's a plane that's parallel to the YZ axis. Just like our line over here was parallel to the y-axis, this plane is parallel to the YZ. Now, with that idea, I want to expand it a little bit and consider this function. Let's think about z equals sine y. And we want to see if we can figure out what that graph looks like. Now, remember what the graph of sine looks like. And I'll just do part of it. Let's see here. We've got the, we'll just talk about the x and the y-axis. Or, well, since it's z equals sine y, this will be the y and the z-axis. So let's see what this looks like if we're not considering x, we're just dealing with the yz plane. Now here is pi over 2. Here's pi. Here's 3 pi over 2. And here's 2 pi. Now remember what this graph looks like. It goes up, hits a maximum here at pi over 2, crosses the axis at pi, has a minimum at 3 pi over 2, and then hits 2 pi again. So if you were just looking at this graph, if you were just considering z equals sine y, this is what the graph would look like. You're not even considering x. But remember, the way we're graphing in 3 dimensions, so you think of x as coming out of this paper. It's going out of this paper and even inside, but there's a perpendicular to this axis is the x-axis. So let's take a look at what that might look like. Okay, so I'm going to do this. Here, remember, is the x-axis, here's the y-axis, and here's the z-axis. And I'm going to just make a little broken or dotted line here. And I'll do this. I'll say, okay, this is, we'll pretend that's pi over 2. This is pi, 3 pi over 2, and 2 pi. And what I'll do is I will just make, I'll see if I can make that sine graph. Okay, so it comes down here, then back up, and there. Whoops. Down a little bit and back up. Okay, so there's sine I. Okay, so there it is. This is what we just looked at in the 2 dimensions. Now let me make another line down here. And what I want to do is I want to identify these where I have the pi's over 2. Okay, there's pi over 2. Here's pi. Here is 3 pi over 2 and 2 pi. Okay. So now I want to graph the function here. So I'm going to go up here, down, back, and up. Okay. Now I can do the same thing throughout here. I start here, go up, down, and back up. And you notice I'm making all these little graphs of sine. Okay, so, and I could do this for a long time. In fact, you know, you could, these just go on forever. But, and I only did a few of these. You realize there's an infinite number, even between each one of these curves, there's infinite more of them. And what forms here is a surface. This is a surface. It's a surface that looks like, you know, the sine graph, but it's a infinitely long surface. It also goes back in the negative direction. But this is the graph of z equals sine y. Now notice these lines I drew right here. These lines are called the rulings. And these rulings, notice, are parallel to the x-axis. Notice my curve up here was z equals sine y. There's no x in there. So that means I'm going along the y-axis. Now, what this graph is a cylinder. Now, you might think of a cylinder, you know, the classic cylinder is just the same, you know, you like a Coke can or something. But we're going to look upon the cylinder a little differently. Now, for our purposes, this shape that was formed here is a cylinder, and some parts I want to identify to you. This curve, these curves, these little sine curves, these are the generating curves of that cylinder. Okay? These lines right here are the railings, and the railings in this case are parallel to the x-axis. Now, so that's how we want to think about a cylinder. And we're going to look at several graphs of cylinders. Let's think about this one. Let's think about z equals y squared. And let's think about how that might look. Now we know in 2 space how that's going to look. That's just a parabola. So if we were dealing with the x and the y axis, it would just look like this. I mean yeah, but so we're not considering x here. We've got y and here's z. So z equals y squared. So you put in the y's, square it, and you get the z's. So it's just like if we had the x and the y. But in this case, the x comes out of the paper. Okay, so the x is perpendicular here. So let's see if we can figure out what that might look like. Let me see if I can draw it here. Now, I'm going to just draw a couple of lines here. See if I can get a representation of what this might look like. Now, first of all, what we're going to get is a bunch of parabolas. So imagine all these parabolas, a bunch of them stacked up, going along the x-axis. That's what we have going here. So I don't know how good of a job I'll be of drawing this, But it's going to look something like this. It's going to be all these parabolas going along the axis so that we just have like a trough there. Well, that's what a cylinder is. This is an example of a cylinder, and this was an example of a cylinder.